Okay. Yeah. Today I would like to present to you our most recent paper on the archive called Quantum LIDAR, or Heisenberg-limited quantum LIDAR for joint range and velocity estimation. And first I would like to explain a little bit the title. So quantum LIDAR is pretty straightforward. So it's basically like a radar which is able to estimate parameters of a distant target by sending electromagnetic radiation. And a radar sends radio waves or microwaves, and the LIDAR sends light or, well, radiation in the optical regime. And yeah, the difference is that at room temperature in the optical spectrum, we don't have thermal noise. Well, in the microwaves, we have a lot of thermal noise. And yeah, that makes a big difference when you construct a protocol, especially the quantum protocol. And well, Heisenberg-limited refers to the fact that our protocol is able to reach the Heisenberg limit. And the Heisenberg limit just means that the error that we make on average, or well, what we also call the mean squared error, scales as 1 over the photon number squared. Yeah. And in the classical world, we usually only get 1 over n scaling. So yeah, in quantum metrology, people usually try to reach this Heisenberg limit. And yeah, we were able to show that we can reach this Heisenberg limit for both parameters at the same time. Yeah, which so far has not been addressed in the literature. So yeah, one thing about our protocol is that it's basically a classical protocol. So the state we are using is almost classical, and the measurement that we are using is a classical measurement. And well, we just put a little bit of quantumness into this classical protocol. And this is why, because our protocol is so similar to the classical one, I would first like to explain to you like the classical LIDAR theory. So, well, a classical LIDAR emits, well, maybe we can turn off the light. Yeah. Well, a classical LIDAR emits electromagnetic signal towards a target, and well, the electromagnetic signal has some temporal properties, or well, it's a function of time, and usually the signals we use in classical LIDARs can be represented yeah, as yeah, like this here. So yeah, we have kind of 2 parts of the signal, a component that oscillates like a cosine with the so-called carrier frequency, and well, this function x of t, and then a second part which oscillates as a sine, and well, multiplied by y of t. And well, these are called the quadratures of the signal. And well, in quantum mechanics, that would be like the position and the momentum. And yeah, we could represent our signal in this kind of phase diagram. So for each moment in time, we can draw a little arrow, which then represents our signal. And this is how we can fully characterize the signal, basically. And yeah, if we look here at the, well, electric field as a function of time, well, it may look like something like this. So we have some envelope here, and this would be described by these x of t and y of t. And then these rapid oscillations, which are due to the cosine and sine function. Okay. Well, and what's also possible is to just well, write this signal as a complex function. So we can make one of the quadratures imaginary, and then we can just compactly write this as a complex function. And well, this is kind of useful for the quantum description, and in general, it's useful. So, okay, this is what we sent to the signal, to the target. And now, well, the signal travels towards the target and comes back. And now we want to know how our signal will be transformed. So, okay. Well, this is what would come back. So here we have like a loss of energy. This square root kappa kind of means that, yeah, well, some of the photons get lost. And then we see also that this s of t function gets a time delay. And this is because, well, our signal has to first travel to the target and then come back. And this whole round trip takes some time, tau. And this time, tau, is related to the distance between the LIDAR and the target. And then we also have some frequency shift here, which is due to the Doppler effect. So if the target is moving, then the frequency of the signal will be shifted, and this frequency shift is proportional to the velocity. And well, in general, we also will have some little noise. Yeah, and this is just described by some function n of t. And well, it's like a random function, but yeah, for now it's not so important. But yeah, this is what you, yeah, this kind of description is what you would literally see in the classical LIDAR literature. Yes. Oh. Okay, yeah, so now we know how the signal comes back. So now the question is, how can we measure this signal that comes back? And well, the most natural measurement is just the measurement of the electric field. But how would we actually do something like measurement of the electric field? The problem with optical wave is that the oscillations are really rapid. So for example, 10 to the 15 oscillations per second. And well, modern electronics cannot resolve such rapid oscillations, but we can kind of down convert the frequency to make these oscillations of the field visible. And this is done by, well, a heterodyne receiver or a homodyne receiver. Yeah, and the main principle of this receiver is that the signal comes back, and what we then do is we mix the signal with a so-called local oscillator. And the local oscillator is basically just a laser beam of a given frequency and some phase. Yeah, and in principle, we can control these parameters, so the local oscillator frequency and the local oscillator phase. And well, then there's this beam splitter, like a 50-50 beam splitter, where we mix those two signals, and then we just measure the energy at the outputs of the beam splitter. And yeah, then we get like two, for each moment in time, we get two energies, and we subtract them, and the subtracted signal is then our measurement outcome for each moment in time.
What operation does the beam splitter do?
Well, I mean, it mixes like the both signals, like yeah, I mean, it's basically like a kind of interference.
It's like a sum.
Yes, I mean, it's a sum of both signals, yes.
The weight of each branch is with phase, or how?
What do you mean, the weight of?
Yeah, how much goes to each output? How is that?
Ah, yeah, I mean, it's like 50-50 each output, so yes. Well, I mean, yeah. Okay. So yeah, this is how this works. I mean, this also works in the quantum world like this, but also classically, we can do something like this. And now, okay, how would our measurement outcome then look like? So for heterodyne, we basically get, well, this is our measurement outcome. For each moment in time, we get one number. And, well, we basically get the signal back. The only difference, so basically we can directly measure the signal. The only difference is that this frequency here, the oscillation and the cosine and the sine are now, well, a different frequency. Yeah. So this is how we can kind of down convert these rapid oscillations to lower frequencies. But we see that we get like a lot of information. So we get the information of this x of t and of y of t of both of the quadratures. So in principle, that looks like a really nice measurement. And this is actually, yeah. What? You want to say something?
I wanted to do a question, but I didn't want to cut your face.
Yeah, I mean, this is the measurement that people actually do in the radar world. And also radios use this heterodyne receivers to, well, down convert the radio frequency to a frequency that you can hear with your ears. Yeah.
So my question was, this down conversion, you need like a phase synchronization between the signal and the local frequency. I mean, if you have like phase noise, is this a problem?
Well, I mean, yeah, the nice thing about the heterodyne is that you usually in practice don't need any phase tuning. So obviously if you change the phase, there would be some small change. So this y of t and x of t would be transformed, like they would be rotated. But because you get both of them, you can still kind of reconstruct your signal. So in practice, yeah, the phase in heterodyne doesn't matter, at least for the applications we are concerned with. But yeah, when we do homodyne, the thing looks different. So in homodyne, we have to match the frequency of the local oscillator to the signal frequency. and we also have to match the phase. So depending on the phase kind of decides which of the quadratures we are measuring. So we can measure X quadrature like here, but we could also measure the Y, or we could also measure any quadrature in between, like some mixture. Yeah, and now you may think, why should we ever use a homodyne if we only get X of t, but not Y of t? And the reason is that in homodyne, your signal to noise ratio is better. So, yeah, you can make more accurate measurements if you just focus on one of the quadratures. But this comes at a high price, and the price is that we need to tune our local oscillator to the signal that comes in. And well, if we want to estimate parameters, well, we kind of already have to know them before the measurement, but okay. Well, okay, so yeah, so this is the measurement, and okay, now we basically have like the whole classical protocol, and now we can do our estimation theory. And well, there's something called the Fisher information, and well, this gives you like the ultimate accuracy limit. Well, after some calculations, we will find that the mean squared error, or the ultimate accuracy limit, is given by this for the time delay. So we have this 1/n scaling that we would expect for a classical theory. Yeah, for both the, well, the time delay and the frequency, or well, for the distance of the target and the velocity. Yeah, so this is like a standard result, basically. Okay, so this is the classical theory. Okay, now our protocol is really similar to the protocol I just told you. Now we have to only make one little change. And yeah, for this we introduce now the quantum theory. So, okay, now we make the step from classical to quantum. And okay, we have this electric field. And well, in the quantum description, this becomes an operator. And we have these commutation relations. Okay. So yeah, this is the first change. And now we could ask ourselves, how does this classical signal, how could we describe this with our quantum theory? And as you probably have heard, for this, people usually use coherent states. So yeah, our classical signal can be described by a coherent state. And well, the form of this coherent state is this. So we have some exponential function, and then inside we have an integral, and there's an operator in the integral. Well, the main message is that this looks a bit, yeah, hard to do calculations with. If you have an integral and so on, well. So yeah. So yeah, maybe one more thing. So this is what we would call the time domain. So we describe our state in the time domain. Like if in quantum mechanics you have like the position domain and the momentum domain, and wait, they are two different bases with which you can describe your state. And the same is true here. So we have the time domain and the frequency domain, but we have also other bases. So we have infinitely many bases with which we can describe this state. And well, So why shouldn't we just take a coordinate basis in which our state looks a bit more friendly? And yeah, this is what we do. So, well, this phi of n is some complete set of functions. Well, basically, those are now our coordinates. Well, it's like a coordinate transformation, basically. And, well, we could choose any kind of coordinate basis, but here in our case, we choose a particular one, which is the so-called Hermite-Gaussian basis. Well, and the first few elements, well, look like this. So the first is just a Gaussian, and the second and third, well, have these shapes. And, well, in this basis, we can rewrite our state. So now we have transformed this integral to a sum. And, well, basically now we can write our state in a really more digestible form. So, yeah, these are displacement operators that just act on a single mode. And, well, now, yeah, everything is more easy now. And, well, this is a nice way to make our lives easier, but also these bases have a really special property when it comes to estimating, like a time delay and a frequency shift. So yeah, there are two reasons why we chose this basis. Okay, so well, we just changed the basis to represent our state in a more easy way. And now what happened to the measurement? Well, basically for homodyne, these quadratures also become operators. So we have now these two operators, x and y, or we could also say position and momentum. And they satisfy this commutator relationship. And whenever we have such a commutator, we know that there's this Heisenberg uncertainty principle. So, and well, basically the Heisenberg uncertainty principle can be now represented with this little circle. So in the classical description, we would just have like this vector, which would characterize our state. But now, due to the fact that we now do quantum mechanics, there's some inherent noise all of the sudden. And, well, we would just represent this as this little circle. And this just means that, well, if we make a measurement, we wouldn't measure like always the tip of the circle, but there would be some noise, some random noise in this kind of circle of a Gaussian shape. And yeah, so this is basically just the Heisenberg uncertainty relationship. And well, if we just look at, for example, x of t as a function of time, this noise that looks like a circle here, as a function of time, it just looks like a white noise. So now, because we made this switch to the quantum, we got this noise. And this noise is what limits our ability to estimate parameters. So, well, if there were no noise, then we could estimate parameters with infinite precision. So basically this here, this noise, or this circle noise, is now our enemy, and we have to fight it. We basically have to get rid of this noise. Yeah. Okay, so, well, I mean, this is again the time domain, but we can do again the same in our new coordinate basis. So yeah, we remember this new coordinate basis, which were these Hermite-Gaussian modes. And instead of using this phase diagram for each moment in time to represent our signal, we can use phase diagrams for each mode index. And by that, we can fully characterize our signal, just in a different basis. And well, we get again these quadrature operators, and we get again these Heisenberg uncertainty circles. And well, okay. But now the cool thing is about the quantum that we can use something called squeezing. So, well, instead of having these circles, we can have like ellipses. And this just means that in one of the quadratures, we can remove the noise, whereas in the other one, we get more noise. So, okay, I mean, this is the only difference. If we go back, this would be like a completely classical state that we have in the classical LIDAR literature. But now with this little addition, we introduce some quantumness here into the mix. Now the question is, can we somehow choose our state in such a way that we can get an advantage? I mean, if we just randomly squeeze something, probably there will be no advantage. But, well, what we found is the following. So if we have a state that looks like this, so the zero mode is squeezed in the x quadrature, the one mode is squeezed in between x and y, and then the next quadrature is again squeezed in the x. Well, and the 3 mode, for example, is just empty. Well, this, well, is enough to get this Heisenberg scaling for both the range and the velocity of a target. Well, and obviously we have infinitely many modes, so we could, yeah, there's a huge landscape of possible states we could look at, and obviously this is not the only state that works, but this is a state that works. And yeah, we kind of found that we need at least 3 modes to estimate both parameters. For example, if we just use the first 2 modes, but not the third, then, well, it didn't work, kind of, for both parameters. Yeah.
So to read an equation, why this allows you to remove the noise?
What do you mean?
So why this squeezing protocol allows you to cancel the noise?
Well, I mean, these modes, they are now squeezed, so there's like a reduced amount of noise along this direction if we choose to measure this direction. Well, if we measure like the y direction, then, well, we would have increased noise. And yeah, I mean, yeah, well, I will come to this later. I mean, this is just a state, but we still have to make the right measurement to make this work. Yeah, so basically we can use the quantum Fisher information again, and we see, okay, yeah, in principle, there's an advantage, but we still have to show that there's also a measurement that works.
Sorry, this is like a squeezed vacuum, or
Yeah, this is a squeezed vacuum, right? So, because, yeah, and actually this is what I wanted to say. So squeezed vacuum is not so practical because usually if you generate these states, they have not so many photons, maybe 1, 2, maybe even 100, but yeah, if you have a classical LIDAR, you have on the order of 10 to the 6 or 10 to the 9 photons. So yeah, to make our protocol more practical, what we thought was why can we not just also introduce some displacement or like a strong, like this, yeah, like in the classical case we had like these arrows pointing, and well, we found that we can also introduce like a strong coherent signal as well, which is, well, also squeezed as we see here. And this actually even gives a better performance than the full vacuum state. And what we also studied was, for example, the case where most of the energy was in the displacement. So most of the energy was like in the classical part of the protocol. And then, even then, we get a nice little advantage just by squeezing the state a little bit. And yeah. So yeah, even if we have like a high power state, we can still get an advantage with a small amount of squeezing. Yeah, okay, this is what we found, and well, then, okay, yeah.
Question about the displacement.
Yeah.
Why you only displace the first mode and the rest stay?
Well, I mean, again, well, I mean, there's a huge amount of things you can do. So you can also displace the 0 mode and the 2 mode, and
These things also rotate, right?
well, it depends. I mean, in this case, no. If you just give me the numbers, like the displacement and the squeezing, then this characterizes the state for all times. Yeah. But I mean, depends what you mean. Well, if you change the basis and so on, they can rotate. But yeah. So I mean, we can also displace the state here or somewhere else. But well, what we found was, okay, we wanted to keep the thing as simple as possible, like a proof of principle kind of protocol. And well, we found that this works. And well, the angle of displacement actually also matters. So if we would have changed the angle, then well, this would have also changed the performance a lot. So yeah, like especially like the angles of the squeezing between modes is really important. So if we would have a different setup, yeah, then maybe the whole thing wouldn't work anymore. Or the whole thing would only work for estimating the range, but not the frequency. Or, yeah, well. And then, okay, now you may think, oh, why is it like this? And, well, one answer would be, okay, you can just do the calculations and see it. Well, another way to explain it is that, well, this time delay and frequency shift, they are like transformations, and they also transform our modes. And what we find is that this Hermite-Gaussian mode basis transforms really nicely. Well, it essentially couples neighboring modes with each other. Well, and then you can kind of understand this whole thing as a beam splitter transformation. And well, we know how beam splitters work, and well, like this we can kind of understand how to design states to extract the parameters. Because in the end, these transformations, the range and the time delay transformation and the frequency shift transformation, they kind of transform the modes, well, in a beam splitter way. And okay, we understand beam splitters, so well, this is one way to kind of begin to understand why we have to choose these angles and not other angles and so on. Yeah, well, I still have to maybe think about a better explanation, but this is the best I have so far. Okay, so yeah, well, so I haven't talked so much about the measurement yet. Well, the measurement is homodyne. Well, and well, the big or like a downside is that we have to kind of know beforehand the parameters that we want to estimate. So we can tune our homodyne receiver to the signal and then measure the right quadratures. Because if we measure the wrong, then we have much more noise, and then obviously we will get a really bad performance. So yeah, we kind of have to match the parameters, but that's not necessarily so bad, because we could think of an adaptive estimation strategy where we have multiple shots, and in the first few shots we get like a priors of the parameters, and then we use this prior knowledge to tune our homodyne device, and then in the later stages we get this really high performance. And well, yeah, the phase matching kind of the error has to be like 1/n, well, which is kind of really a costly, well, it costs a lot of energy to, well, okay, I mean, it's hard, but yeah. And okay, we also looked at photon loss, and okay, the cool thing is that even if we lose like 50% of the photons, we still have an advantage compared to the classical protocol. So, okay, now 50% photon loss, well, that means that, well, in usual LIDAR applications, you lose almost all of the photons. So, for example, if you try to estimate the distance of a plane, well, you lose almost all the photons. But yeah, I mean, maybe our protocol could be used in a laboratory somewhere where we have a lot of control and so on. And compared to the previous protocols, this is much, much better. So the previous protocols, they lost their advantage with the loss of a single photon. And I mean, we can lose maybe 1,000 or whatever photons. As long as it's 50%, we are good. So, yeah. Okay. Well, that's it. Yeah.
Yeah, so yeah, what I understood is that then, for example, this protocol in practice will be usually, for example, you have some kind of previous estimation of the location, and then you can just focus a little bit the beam.
Yeah.
And I guess that it's difficult, but maybe I have some spoilers that you are working now on being able to design a protocol which doesn't have this previous knowledge and where you don't have any information about the location. have been tried this?
You're asking, this has been tried, or yeah, I mean, I'm actually now working on this, or I mean, I also wanted to, yeah. I know, I mean, there has been some previous work on this actually, and I also gave a talk about this, where I presented like a paper from Schwang and Shapiro. I mean, this is already a lot of time ago, but yeah, I mean, there's some, yeah, always the question is, so all these protocols, they work if you have a good prior information. So if you already know more or less the parameter. And then, well, the question is, can we also do it when we don't know the parameters? And, well, either you find like a specific protocol, and then you can just analyze the protocol and see if it works or not. Or you could also design some kind of bounds that kind of maybe tell you if it may not work. Yeah. I mean, there's a way to construct bounds in a way where you can say, oh, well, the protocol should work in this range of parameters, and in that range, well, I don't know where it is, the parameter. And yeah, so I mean, there are some techniques that could give you like more insights about more realistic global estimation protocols.
And which is the good studies? I mean, for example, in 3D would be to consider the solid angle, I mean, the uncertainty, the solid angle that you have, where the object can be located or something like this, or maybe 2D is here with the angle, the size. I mean, this, just that these are interesting. Here,
yeah, I mean, this is like, I mean, in this protocol, we haven't really considered like this, like the spatial features of the light. We kind of assume that the beam just travels without diffraction, but yeah, I mean, there are also other protocols where, like, you try to locate the target in a 3D space and so on. But, yeah, I mean, at the end, you just, there's some bounds like that you can calculate, and they may tell you if your protocol fails. And well,
so fail means to not reach the Heisenberg-limited.
Yeah. So, yeah, I mean, if you know the parameters, then you can reach it. But let's say you don't know, and your uncertainty is like maybe that big, maybe then it doesn't work anymore. And yeah, there's some kind of bounds one could calculate, and they could kind of tell you, does it work or does it not work? And yeah, this is like now like a new thing that recently there was a paper on that, and so yeah. Also the Schwang and Shapiro, they did this, so now would be interesting to see like, okay, how well the performance changes when I change my assumptions about the prior information. Yeah.
I have seen that in the classical case and in the quantum case, low performance, while estimating the position and velocity depends on the I think frequency width and time width.
Yeah.
So in principle, you can make both things as big as you want, or it's not like that.
Yes. Well, this is like the bandwidth, and this is the time duration, how this is called. Well, and this product, or yeah, both quantities can be made as big as you want, but you cannot make them as small as you want. So, like the product, well, is lower bounded as well. Yeah.
But you want them to be big, right? To have like small.
Well, yeah, I mean, I don't care so much about like what this actually is. I just want this to be the same for the quantum and the classical. And then we say this is a fair comparison because they use the same time duration and the same bandwidth and the same energy. So this to me seems like a fair comparison. Yeah. Yeah.
I saw something like in LIGO, they were using some squeeze like states, right, to improve precision. So, how is it related somehow to this kind of ideas?
Yeah, I suppose it is related. I mean, LIGO is an interferometer, and in an interferometer, usually you measure like the phase or some phase, and well, a phase can also be related to a distance, for example. But the problem is, whenever you have a phase, there's like some ambiguity. So a phase shift doesn't just tells you like a little change of length, but you cannot like estimate big changes because there's this ambiguity of the phase. So yeah, in the sense, the interferometer also needs a lot of prior information, kind of, and I mean the whole, like this whole setup looks like a really similar to an interferometer, right? But yeah, but I mean there are differences, yeah. I mean, it's really related, but it's kind of different because, yeah, it's just different.
In your previous work about the radar, you just needed to use entanglement and squeezing, but so the state you were preparing was somehow easier. Because I don't see how easy it can be to prepare this state with the displacement operator only on one mode. Is there an easy way of doing so, or?
Yeah, I mean, first of all, yeah, I kind of forgot to say that, but yeah, I mean, basically, these states here can be actually produced in a laboratory. Well, yeah, as it turns out, this mode basis is really natural for some physical processes. And, well, basically how this works is that you have some material, some crystal with special properties, and then you, well, send a coherent or strong coherent state through this crystal, and at the end comes out like a squeezed vacuum state, this squeezed vacuum state. Well, but well, as far as I know, all the squeezing angles are in just one direction, but I suppose you can somehow adjust things. So yeah, these states, they can be produced, and well, then displacing the state can be also realized fairly easily. I mean, yeah, you can displace states with highly translucent beam splitter, for example, and yeah, I mean, there's no problem to displace this thing as well. Yeah.
Last question, very last one. Can you go to the last slide? Well, and how the question point depends on the displacement. So obviously keeping margin is better than how this crossing point depends on the squeezing on the displacement protocol.
What a crossing point?
Okay, the classical one. So the blue line.
Well, here or here? Well, I mean, one thing I haven't said is that here in this diagram we kind of optimized the allocation of squeezing and displacement. So yeah, we kind of had to pick like the optimal ratio between squeezing and displacement. And well, for each point we kind of optimize this, and yeah, and usually it's beneficial to have more displacement. Well, especially as you go towards high losses, well, then yeah, well. But yeah, I mean, maybe there are states that could be even more loss resilient. I mean, you can design the states really, I mean, yeah, you can try to maybe find more optimal states for certain tasks, or yeah, maybe there's something that's way more loss resilient, but I'm not sure.
Okay, thank you very much.